Hello all, my name is Ritvik and today I'll present the paper Evaluating River Networks Resilience using topological analysis through a complex network approach. The central idea of this network is to treat a river system as a network of nodes and edges and then ask how does the structure of that network affect the river's ability to handle floods and recover from that floods afterwards. In this talk, I'll explain the motivation, why river network resilience matters, and then I'll briefly cover the background concepts from hydrodynamics and complex networks, and then explain the methodology used in this paper, walk through the main results, and then finally discuss some strengths, limitations, and possible future directions. So, why we have to study network resilience? This paper starts from a simple observation where modern river networks are heavily modified while extreme floods are becoming more common. Small structural changes like closing a few channels can have a big system wide effects on the peaks and flood duration. Traditional hydrodynamic models don't capture how network structure itself controls resilience. So the authors wanted to ask how does river topology shape flood resilience and which reaches are structurally critical. So let's see some background of complex networks. So this is a sample network where the dots are the nodes and the lines represent the edges, as you can see in the picture, and the direction is the arrow mark represents the flow direction. So the edges are represented by E and standard notations. So before going into the method, um, on the hydrodynamic side, uh, a flood is modeled as a disturbance moving through this network, and the model gives us the water levels over time. Resilience here means keeping peaks low and recovering quickly after the flood. In the rest of the talk, we'll see how the authors connect these network metrics to those resilience indicators. So here are some hydrodynamic resilience indicators. To make resilience measurable, the authors define four indicators based on water level dynamics. PL, which is peak water level during the event, which is the flood. Event here is flood, and LR is how fast the water level rises, which is represented by rise of water level, and LD is how fast it falls afterwards, and FD is how long the water level stays above some particular threshold. So lower peaks or slow rises and faster drop or shorter duration all correspond to a better resilience. So if you have a lower peak, then the water level is very low. If you have a slow rise, then the water level is standard. If there is a faster drop within the threshold, then it's a good resilience. These quantities are computed for every reach and then summarized as averages and maximum values, like represented by PL and FD to capture the network's worst case response. As you can see in the picture, at T2 and H3, the water level is peak, which is the indication of flood. So let's see the methodology which has been used by the authors. Here is the overall workflow of the paper. First, the authors represent both an idealized river, which is a general assumed river, and then a real Wuxi river as networks, and then generate many alternative topologies by disconnecting different sets of reaches. Second, for each configuration, they run the same flood simulation with a 1D hydrodynamic model and compute four resilience indicators, which is peak level, rates of rise and drop, and flood duration. At each reach, then they summarize them at every reach. Third, they compute network metrics for each topology and use correlation, which is PLS SEM model, and its centrality to see how topology controls resilience and which reaches are structurally critical. The next slides go into the topological metrics and networks analysis more in detail. As you can see from the pictures, these are the red lines are the indicators where if we break that particular, that is a peak, and if we break that particular node or edge, then it's more uh, frequent to occur, the floods to occur. So proceeding to the next slide, these are some different river network configurations. The author used 8 standard metrics from complex network theory. First, connectivity metrics. We'll see connectivity metrics. If the average degree and link density are high, which is D and capital D, it means many junctions have 3 or 4 channels meeting instead of just 2 channels. For example, a dense canal network in a city would have a higher average degree than a simple single main river with a few tributaries. And then the measuredness coefficient tells us how many loops there are in a particular canal. Imagine a ring canal around a city. If one branch is blocked, then water can still go around the loop. So a tree-like river with no loops has low measuredness. So a single cut can isolate parts of the system. The next one is single degree nodes, which are the dead ends. Think of a small side channels that connect to a main river at only one point. These more of these have like the more parts of the system are hydrodynamically hanging off the main network, which is because it's a dead end. And then let's see the robustness metrics, which is network efficiency and average shortest path length. A compact grid-like river network where water can reach any point in just a few steps has high efficiency and low path length. A narrow river with few shortcuts has low efficiency and long paths. Then comes the algebraic connectivity, which is lambda 2, is a classic measure of robustness. A highly lambda 2 means you would need to remove many reaches before the network splits. For example, a highly looped network which has many loops with multiple parallel routes will have higher algebraic connectivity than a simple chain of river. And then later we'll discuss a few case studies which the authors discuss. So metrics like lambda 2, efficiency, and path length are strongly associated with how the network absorbs and recovers from the floods. So let's see the first case study, which is an idealized reticular river network, which is assumed the all the these are like this is an assumed river network. In case study 2, we'll discuss about a real river, which is called Buxy River. So the first case study uses an idealized river, a kind of synthetic grid of channels with one inlet and one outlet. Like it's a simple one. All the reaches have same physical properties like length, width. So when the authors modify this network, the only thing that changes is topology, which means the reaches are disconnected or connected. They create many different configurations by cutting specific reaches, but they always keep at least one path between the inlet and outlet. For example, disconnecting a central cross channel versus disconnecting a peripheral branch can lead to a very different flood responses, even though the total number of remote branches is the same. This setup is perfect for asking like if we only change the network structure, how does that affect peak levels or flood duration and overall resilience, which we'll discuss later. So in the idealized grid network, the author systematically remove reaches and watch how both topology and resilience change. Structurally, as we cut links, the average degree, clustering coefficient, link density, efficiency, and then algebraic connectivity, all of them drop. While the number of dead end nodes and average shortest paths lengths go up, that describes that a network is less connected and less compact. So, hydrodynamically, these changes matter a lot compared to the reference network. The maximum peak water level PL can increase about 12%. The maximum drop rate, which is LD, can fall up to roughly half of its original value. And the flood duration can become about 3.5 times longer. So, the same flood input leads to higher peaks and much slower drainage when the topology is degraded. Interestingly, the rise rate LR doesn't correlate strongly with topology because its correlation is around zero point 0.2, which is very less because it's controlled by a single local reach. In contrast, the drop rate, which is LD, has correlation around zero point 0.7 with the network metrics, so it captures the overall network level recovery much better. This tells us that some resilience indicators like LD and FD are more informative about global network resilience than others like LR, which is water level rise. So, to organize all the metrics, the authors build a structural equation model with three latent variables, which is connectivity, robustness, and resilience. Connectivity is based on how many links and loops the network has and how many dead ends it avoids. Think of a network with lots of cross channels and a few dead end side arms. Robustness is based on efficiency, path length, and algebraic connectivity. So, a network where water can take many short routes and where cutting a few reaches does not split the whole system. The model shows a strong positive path from connectivity to robustness and a strong negative path from robustness to resilience indicators like peak level and flood duration. In other words, a more robust network tend to have lower peaks and shorter floods. The direct path from connectivity to resilience is much weaker, so connectivity mainly matters because it creates a robust structure. This justifies focusing on robustness metrics like lambda 2 and efficiency rather than just counting the links in a network. So next, the authors ask which specific reaches are structurally most important. They compute an integrated edge centrality index over the idealized network, where which is the figure shows that the central reaches have highest strength centrality because most shortest paths and most flows pass through that central zone. Corner reaches have very low centrality and act like peripheral side paths. Then they compare three different configurations that all remove the same number of reaches. So the basic connectivity count is identical. However, uh, their robustness and resilience differ. In case 2, where some disconnections occur near low centrality corner reaches, the flood duration becomes about 1.7 times longer than the reference case, giving the lowest resilience. And then in case 3, where connectivity at the outlet and inlet is preserved and cuts are placed uh, more carefully, the network actually shows the highest resilience among the three. This shows that it's not enough to just count how many links we lose. Resilience depends on where those links are removed, especially relative to high centrality zones and to boundary reaches like inlet and outlet. So let's proceed to second case study, which moves from an idealized grid to a real plain river system. As you can see in the picture, this is a Wuxi River network in the Yangtze River Delta. It's a dense braided network in very flat terrain, so there are many interconnected channels. For modeling, the authors keep only channels wider than 20 meters and end up with like 115 reaches including 7 inflows and 6 outflows. As you can see, the inflows arrows are going into the system and outflows arrows are going out of the system. All reaches are simplified as rectangular channels with lengths between about 500 to 6000 meters and widths between 20 to 100 meters, and zero bed slope. There is no slope at all. Starting from a fully connected reference configuration, they generate 50 alternative topologies by disconnecting selected reaches, representing changes due to gates or pumps, because water levels vary a lot across the network. They switch from a single fixed warning level to an adaptive one. For each reach, the threshold is 90 percentile of its maximum water level under some reference conditions. Then they run the same kind of flood simulations and compute the same four resilience indicators as before. Let's see that in the next slide. So for Buxi River network, the author repeat the same analysis. For each of the 50 configurations, they compute the topological metrics and resilience indicators and compare them. They find that the metrics like average degree clustering, link density, and network efficiency, and lambda 2, which is algebraic connectivity, all have the strong negative correlations, meaning that more interconnected and robust topologies tend to have lower peaks and shorter or faster decaying floods. In contrast, the number of single degree nodes and average shortest path correlate positively with vulnerability. The special, like the gap, again performs poorly and doesn't show a consistent relationship. Overall, the trends are similar to the idealized case, but the correlations are slightly weaker, probably because the topological metrics ignore actual reach length and width, which still matters for the hydraulics. In contrast, the idealized case, the highest centrality is concentrated in the middle of the network where many inflows and outflows are linked. These central reaches act as structural bridges in the network. The most shortest paths and a large fraction of flow pass, the water passes through them. So when they compare scenarios with the same number of disconnected reaches, higher centrality reaches causes much stronger deterioration. Like because Wuxi River has many inflow and outflow boundaries, individual boundary reaches, and they are not as dominant as the internal bridge reaches, which largely controls the system resilience. This reinforces the idea that centrality based analysis can help identify which real world channels should be prioritized for protection or careful operation. So, how this can be used in practice? In terms of impact, this framework gives water managers a way to go beyond local checks. They can pinpoint critical bridge reaches with centrality, test proposed gates or closures by editing the network, and use global metrics like algebraic connectivity or efficiency as quick indicators of how robust the whole system is. That makes it easier to prioritize maintenance, restoration, and design choices that improve flood resilience at the network scale. So let's see the strengths and limitations of this paper. This paper has several Strengths. It really combines complex network theory with full hydrodynamic simulations, uses a idealized tested bed to isolate topology, and then checks a real network. It also looks at multiple resilience indicators and uses several analysis tools, which gives us a coherent picture. At the same time, there are limitations, like the topological metrics still treat all edges abstractly, like they don't encode physical heterogeneity like roughness or storage. Infrastructure operations are modeled as fixed disconnections instead of dynamic gate schedules, and they mostly look at one flood scenario without a fully uncertainty or multi event analysis where different events are going on at the same time. So the framework is powerful, but still, it's a first step. So to wrap up, the main message is that river network topology really does matter for flood resilience. Metrics like efficiency and connectivity give us an impact to summarize robustness, and edge centrality helps find the reaches that matter most. Going forward, a natural extension is to bring more physics into the graph, model dynamic operations, and test multiple events and hazards. But even in this current form, this framework is useful starting point for system level thinking and river management for the river managers. So that's it for the presentation. So thank you.